Hi everyone, I am Madam Rosmaya. Welcome to my YouTube channel. In this video, we are going to discuss on the topic on semester 3, transition in the energy level. Refer to the animation given here. The electron in an excited hydrogen atom would only stay in the excited state for a duration of a few nanoseconds. The electron would then jump down to a lower energy level. Okay, according to Bohr's theory, the frequency f of an emitted photon is given by hf equals to ei minus ef. So h is a Planck's constant, ei is the energy of the initial state, and ef is the energy of the final state. So from the equation just now, we can calculate wavelength. So f is c per lambda. We substitute into the equation. So cross multiply, we get lambda equals to hc per ei minus ef. Okay, so lambda is the wavelength. Okay, so the wavelength lambda of the photon emitted from a hydrogen atom is given by from this equation. Okay, so we factor out 1 per lambda, and then we cross multiply. So hc to the right side. Okay, we rearrange these equations like this. Okay, so we can use the equation of ei. Okay, initial level from the ground state is negative 13.6 per Ni squared. This is initial state. Then the final state is negative 13.6 per Nf squared. Okay, then the equation here, 13.6 per N squared is in electron volt. The unit is in electron volt. So to convert to joule, we multiply by 1.6 times 10 to the power of negative 19. Okay, so both energy we convert to joule. Okay, next we factor out the 13.6. Okay, so in bracket leaving 1 per Nf squared minus 1 per Ni squared, because the negative here plus. So we bring this to the front, plus, then minus 1 per Ni squared. Okay, the next step, we factor out 13.6. Okay, then this 13.6 divided by the Planck constant times the speed of light, c, will give you a constant called R, Rydberg constant. Okay, so we can calculate the Rydberg constant. Okay, 13.6 times 1.6 times 10 to the power of negative 19. Okay, per hc. So the Planck constant and the speed of light. So we get the value of Rydberg constant R as 1.0974 times 10 to the power of 7 per meter. Okay, the unit is per meter. Okay, so who is Rydberg constant? The Rydberg constant here, the constant here is named after one of the scientists. So this is the scientist named Johannes Rydberg. Okay, born in 1854 and died 1919 at the age of 65. Okay, so we are going to use the wavelength formula just now, the equation just now, to calculate the wavelength of the photon emitted, okay, or absorbed. In this case, in the transition of the electron in the hydrogen atoms. So at any instant, the electron in the hydrogen atom can only be orbiting the nucleus in one of these energy levels. Okay. Okay, next we are going to calculate the wavelength using the equation just now. Okay, this equation, wavelength equals to hc per ei minus ef. Okay, first from 2 to 1, from 2 to 1, and 1 here and 2. So the energy calculated in the previous lesson, okay, this one we've done already, so we just use this value of energy. Okay, using the equation 13.6 squared divided by n, 13.6 divided by n squared, and we get all this. So 3.40 to 13.6 to 3.40. Okay, so we substitute the Planck constant 6.63 times 10 to the power of negative 34. Then speed of light 3 times 10 to the power of 8. So the energy at N2, level 2, 3.4. And the ground state 13.6, the energy is 13.6. And divided by 1.6 times 10 to the power of negative 19. Okay, because this is in electron volt. Okay, so to convert to joule, so we use this 1.6 times 10 to the power of negative 19. Okay, so the answer is 1.22 times 10 to the power of negative 7 meter. So this is the wavelength. Okay, convert, we use prefix form nanometer. Okay, nanometer, convert to nanometer. So we get the wavelength 122 nanometer, E2 to E1. Okay, so next we do the same for E3 to E1. So for E3 to E1, here we substitute 1.51 electron volt. Okay, so the energy at N3 is 1.51 electron volt. So we get wavelength 1.03 times 10 to the power of negative 7, convert to nanometer, 103 nanometer. So for E4 to E1, here 0.85. Okay, we get 9.7 times 10 to the power of negative 8 meter, convert to nanometer, 97 nanometer. Then E5 to E1. So E5 is 0.54 here. So convert to nanometer, we get 95 nanometer. And the wavelength, okay, when the energy drop from, and when the electron drop from 6 to 1, so 0.38 electron volt here, substitute into here. So is 6 to 1. So we get the wavelength emitted is 94 nanometer. So these are all the wavelength emitted. So this wavelength is not in the visible range. Visible range is between 400 and 700. So the values here is in between 100 to 400, about this range. Okay, here to 200. So in this range. So they are in the UV range. So for UV range, the series is called Lyman. Okay, Lyman series. The wavelength of the emitted photon due to the transition of excited atoms to the ground state results in the Lyman series. Okay. Okay, next, what is the values for wavelength when the transition is from upper level to the E2, to the level 2, okay, N2. So that's mean 3, 4, 5 and above, here until 6, 3, 4, 5, 6 to level 2, all drop to level 2, the electron drop to level 2. So we are going to calculate the wavelength of the emitted photons due to the transition of excited atoms from n larger than 2 to n equals to 2. So we use the same equation. So we start with 1.51 here because N3 1.51. So N2 is 3.4. So here is 3.4. So we get 6.54 times 10 to the power of negative 7 meter, convert to nanometer. So 654 nanometer. For 422, so at 4 is 0.85 and 3.4 is at N2. The net energy at N2, 3.4. So we get 4.7 times 10 to the power of negative 7 meter, convert to nanometer, 487 nanometer. So E5, E6 to E2, here done for you already. So E5 to E2, 434. Okay, E6 to E2, just now 411 nanometer. Okay. So this value lies in between 400 to 700. So it's in the visible range. Okay. So this series is called Balmer series. So the wavelengths of the emitted photons due to the transition of excited atoms from n larger than 2 to n equals to 2 result in the Balmer series. So this is Lyman series, this is Balmer series, and another one is Paschen series. Paschen series not lies in the visible series. The visible wavelength is a non-visible wavelength but larger than 700 nanometer. Okay. Compared to Lyman series is less than 200 nanometer. And the Balmer series for larger level also will result in the non-visible series wavelength. Okay, so Balmer series involve two series. So the non-visible and the visible series, the lines, the spectrum form. Okay. Okay. So this is in the form of energy diagram, energy level diagram. So this is Lyman series from n higher than ground state, drop to the ground state. Here the transitions involve from higher level to n2, and Paschen series involve for n larger than n3, drop to n3. So that's all for the topic transition of the energy levels. Okay, thank you for watching.